Consider the homogeneous reaction involving gaseous reactants and products. Then we can write the Gibbs free energy change of a reactant or product as the Gibbs free energy change at a given temperature plus the universal gas constant by the temperature in Kelvin by the natural log of the partial pressure. So for reactant I, we have the following expression for the Gibbs free energy, and for a product I, we have a similar expression. So therefore the free energy change of the reaction is equal to the free energy change at a given temperature plus RT by the natural log of the reaction quotient. And I'll leave this for you as an exercise where you subtract the free energies of the reactants from the products and group the log terms together and apply some rules for logarithms, and you'll see that the reaction quotient is the partial pressures of the products over the partial pressures of the reactants. Now at equilibrium, the Gibbs free energy change is 0, and therefore we obtain the following expression for the Gibbs free energy at a specific temperature, where the reaction quotient is replaced by the equilibrium constant. And generally, if the equilibrium constant is greater than 1, then this term is positive and delta G naught is less than 0, and therefore the reaction favours the products. Whereas if K is less than 1, then this term is negative, and negative by negative is positive. So in this case the reactants are favoured. And the case where the products are favoured is where the reaction is thermodynamically favoured. And when the equilibrium constant approaches 1, then this term approaches 0, and so does delta G naught. In the case where the equilibrium constant is much greater than 1, then delta G naught would be significantly less than 0, and the products are strongly favoured. And you can apply some algebra to solve for the equilibrium constant to get the following expression. Well, you can draw similar conclusions on the effects of delta G naught on the equilibrium constant. Calculate the equilibrium constant for the following reaction at 25 degrees. So remember the relationship between the standard Gibbs free energy change, which is equal to minus the universal gas constant by the temperature by the natural log of the equilibrium constant. And then if you divide through by minus RT and take e to the power of both sides, we get a relationship between the equilibrium constant and the Gibbs free energy change. And now if we make our substitutions for the Gibbs free energy change, which will convert to joules per mole of reaction, and we divide this by R, which is joule per mole Kelvin, and we multiply it by the temperature in Kelvin. So the Kelvins cancel, and we can convert this as 1 mole of reaction per mole of nitrogen gas, as the universal gas constant is applicable to any gas. So this mole of gas, which we can write as moles of nitrogen, cancels with this one, and then these units cancel and joules cancel, So calculating this out, we obtain the following equilibrium constant. So the reaction strongly favours the products at 25 degrees, but we need to make a compromise because if the temperature is too low, the reaction will be too slow and under kinetic control. At what temperature does the following reaction change from being thermodynamically favoured at equilibrium? We'll recall that the Gibbs free energy change of the reaction, which we can denote using this subscript, is equal to the enthalpy change of the reaction minus the temperature in Kelvin by the standard entropy change of the reaction. And here we assume the standard enthalpy and entropy changes are independent of temperature. So the reaction changes from being thermodynamically favoured, which is towards the products, to thermodynamically unfavoured, is at equilibrium, when the Gibbs free energy change of the reaction is 0. So we substitute the standard enthalpy change, and we have the unknown temperature in Kelvin multiplied by the standard entropy change, which we convert to kilojoules per Kelvin mole of reaction. And now if we solve this equation for T, you're going to get cancellations between the kilojoules and moles of reaction. So if we calculate this out, we get a temperature of 464 Kelvin using 3 significant figures.